Okay, well, welcome to day 2. And if you read through the protocol, day 2 and day 3 are kind of lumped together. So there's kind of 3 big things that you're doing. One is the ultrasound, and that's the actual imaging of the particles that you made in day 1. The second 2 are characterization steps. So one is SEM. And so you've learned a lot about SEM during the instrumental module, so I'm really not going to record anything for the context of this experimental module except to give you the data. So SEM we can pretty much largely consider to be done. And then C is another type of size analysis. So we already did DLS. So DLS, again, we're just going to give you the data because you've spent a lot of time doing DLS already. But I'm sorry, the fourth one, I misspoke. There's 4 steps to this, is an additional type of analysis known as multi-wavelength nanoparticle tracking analysis, or MANTA. And so we're going to come to this later in day 2, but for now we're going to focus on the ultrasound imaging. Okay, so let's just talk a little bit more. In the lecture overview, I talked about this quite extensively, but the first thing we're going to do is remember at the end of day 1, we had 3 little tubes, and so now they'd have dried particles in the bottom. And so now we're going to measure the final mass. So M1 final, M2 final, and M3 final. And know our mass of particles, and we know the volume we added, so we're going to get a concentration of particles in milligrams per mil. See if I can get a better marker. Okay, great. So now that we have this concentration in milligrams per mil, the ultimate goal here is to measure how does the ultrasound signal change as a function of concentration. And hopefully, more concentration equals more signal, right? We should see that. You're going to look at, I think it's 5 concentrations. So one is going to be the 0. And at the 0 point, like all measurements you make, you should be making replicates, right? So at the 0, you're going to have a mean and a standard deviation. At concentration 2, a mean and a standard deviation. Concentration 3, a mean and a standard deviation, etc. Okay? So what are these concentrations? Well, that's the first calculation you're going to have to do, right? By knowing the final mass, you're going to know this concentration. This is the concentration of your stock solution. So remember this big tube from yesterday? It's the concentration that was in this tube, right? This is the sample that we sonicated and resuspended. We centrifuged it before that. So this is your highest concentration. This one, I think I say dilute this 1 to 2. This one's 1 to 5. This one's 1 to 10. Okay? So what do we mean by this? So this is going to be 2 parts total plus 1 part of sample. So what would that look like? How would you actually do this? Well, one part of your sample that you're diluting is the stock solution, right? So one way to do this would be 100 microliters of stock plus 100 microliters of whatever you're diluting it in, or water. So 2 parts total, 1 part sample. A 1-to-2 dilution factor. Here, you would do 100 microliters sample plus 400 microliters of water. These numbers aren't that important. We could have just as easily said 1 milliliter of sample plus 4 milliliters of water. This would still give us a 1-to-5 dilution factor. Okay? So stock solution, a dilution factor 1, dilution factor 2, dilution factor 3, and finally this is only your diluent, so only water. Okay? So these are the solutions that you're going to, or that I am going to make and have you watch me make them. Okay? So let's talk a little bit more about what that's going to look like. Where's my eraser? So you're going to put this into what's known as a phantom. You'll see this pretty quickly, and I showed you this in the intro lecture, where your samples are going to be in here. So these are your different samples, and you're going to take your ultrasound transducer and boop, put it on the sample and image it. And when you image it, if this is your Petri dish now looking at a cross section, you're going to see the background and you're going to see your sample. Okay? And so what you're going to do with image analysis is to draw what's known as a region of interest or an ROI. So this is going to be digital data, right? So each pixel here is going to have a value of what to what if it's an 8-bit image. 2 to the 8th is 256. So every pixel here is going to have a value of 0 to 255. Okay? So if you take this image and you open it up in image J or whatever you're using for image processing and you put your cursor right here, it's going to tell you the intensity of that pixel. And if you move it over here, it's going to tell you the intensity of that pixel. Right? Images are made of pixels. What you're going to do is image the pixels over that entire value. Okay? And there's a lot of different ways that you could describe the pixels in there, right? You could talk about the mean. You could talk about the median. You could talk about the max. What's the highest pixel? What's the lowest pixel? You could add them all up. Right? I think for the purposes of this, the mean is probably the most useful, but you should be aware of there's a lot of information that you could get out of this. You could plot it as a histogram, right? You've got options because there's a lot of data in images. There are a lot of data in images. So that's what we're actually plotting on this axis. We're plotting the intensity, the mean intensity of the pixels that are in that image. Okay? And so hopefully, as there are more and more particles, there's more and more ultrasound being backscattered, and therefore more signal. Okay? One other calculation that you're going to be asked to do is to estimate the limit of detection. So there's a couple different ways that we could do this. One, we could make, instead of 1 to 10, we could make 1 to 20, and then 1 to 21, and then 1 to 22, and then 1 to 23, and just keep going down and down and down until there's no difference with our water only. But that's kind of a hassle. So what you can do is use statistics to estimate using this line. Okay? So if we assume that this is y equals mx plus b, we know our blank has a mean plus or minus a standard deviation. So those are b's, the mean of the blank, standard deviation of the blank. Okay? Now, if you recall from statistics that 3 standard deviations generally gives you 95% confidence, if you think back to a Gaussian curve that has an x bar, 95% is between plus 3 standard deviations and minus 3 standard deviations. So therefore, if we take our y value and go up 1, there's 2, there's 3 standard deviations, and come over to this line and back calculate down, this is the calculation, the concentration that gives us 95% confidence that we can reliably detect it. So what you're going to do is take x, the mean of the blank, plus 3 standard deviations of the blank. You're going to have this data and simply solve for x. And this value is going to be your limit of detection. Okay? Now, when can this fail? Well, it can fail if this is not a straight line, right? That's the easiest way that it can fail. For example, if there starts to be some kind of plateau, then your line, if your line isn't straight, you're not going to have, you can almost get a negative limit of detection. So what you may have to do when you do your data analysis is plot this between a smaller number of data points, right? And in the extreme situation, you just have to do a ratio between the lowest one that you can detect and your background, and do a ratio between those two. But I think we will get good enough data that you can use this approach to determining your limit of detection. Okay? So let's then transition over to actually making our sample to do the imaging. Okay, so remember how we put our particles in here to dry. I'm going to take them out, and lo and behold, they have dried. So hopefully you can see how There are dried particles on the side, but all the liquid is gone now. And I want to try to be a little careful that I don't touch these just because the oils on my hands can change the weight. So if we walk over to the balance, we can obviously start recording these final values. And we'll be sure to get you these along with the other data. So I'm now on step 7D on the protocol if you're following along, and we're going to make these different dilution factors like I talked about on the board. So again, like I said, the exact volume is not particularly as important as the dilution ratio. So I know that I'm going to need about 200 microliters. So I'm going to make at least 200 microliters. So on my 1 to 2 dilution, I already put in 100 microliters of water, and so now I'm going to add 100 microliters of my sample. This is my stock sample from earlier. Similarly, I already transferred 400 microliters to here. So another 100 microliters, and I already transferred 900 microliters here. So another 100 microliters. Okay? I'm going to have one sample that's my undiluted stock. So again, I want 200 microliters. And so there's 100, 200. And then finally, I have a sample that is just water, okay? So hopefully you can kind of appreciate the differences in color from high to low. So this one is clearly more dilute than these higher concentrations, okay? So now that my samples are ready, the next thing I'm going to do is start to make the phantom. So the phantom is going to go into a petri dish like this, and the first thing we need to do is prepare our agar. So let's walk over and weigh out about a gram of agar. Okay, so we're now on step 8 if you're following along on the protocol, and so we need about 100 mils at 1%. So agar is kind of amazing stuff. It's made from seaweed, it's a sugar, and it's a powder that can be dissolved in liquid. It's not very soluble when it's in water, unless you boil it. And then when you boil it, it's completely soluble, and it just looks like thick water. But what's remarkable is that cools back down, it forms a solid, okay? So I think I told you we need 1%. So if I need 1% by weight, and I want to make 100 mils, how much do I need? The answer is 1 gram, right? Because 100 mils of water weighs 100 grams, and if I want 1% by weight, 1% of 100 is 1 gram. Okay? So and the good news is this is not necessarily a super precise determination. If this is 1% or 1.1% or 0.9% agar, it's not really affecting our sample because this is going to be consistent across all of our samples. So, but I'll be sure to record this as 1.066 grams. So then we can just carefully transfer this. And then I'll just go ahead and add 100 mils of water with a graduated cylinder. Okay, so you can see that this is not really dissolving, right? You can see that I've got this powder in the liquid and that you can see kind of chunks on the side. So what you have to do is boil it. There's many different ways you can do this. Well, there's only a few actually, I guess. One is a hot plate, which isn't a very efficient way of doing it, so we can just microwave it. The one thing you have to do is not have the lid tight though, right? Or else you're gonna make a bomb. So the lid can just sit on there gently, and then I generally go for like 1 minute and then swirl it, and then another minute and it should be completely dissolved. So. Okay. Okay, so this is what it looks like then after we have completely microwaved it, and you can appreciate that it's completely transparent. So what we're gonna do now is just gently pour this into the plate. Now I need some kind of little sample holder to place my samples. So what I'm gonna use are these pipette tips. And I'm just going to put these pipette tips in upside down, because these are going to make little holes as the agar continues to cool down. And after the agar is completely cool, we can pull out the pipette tips and we'll be left with a little hole in the agar. The hardest part about this is not getting them to do static electricity with each other. There's not a lot you could mess up. You don't want them super close to the edge, just because it's going to be harder to image. But this looks pretty good. So if we let this cool for a minute, you'll see how the agar looks when this is done. So this is after the sample has now cooled, right? So it's so hard and solid that it's holding these pipette tips in vertically, right? So I don't know how well you can appreciate it. It kind of feels like a gummy bear. And so what happens when I remove that pipette tip is I'm kind of left with a little hole. And that's where my sample's going to go. So fast forward to removing all of these. Sometimes it comes out right away. Other times you kind of have to poke it. Okay, so this is what it looks like after I've cleaned it out. And so we've got these nice little holes that we can put our sample into. Okay? So the next thing, if you're listening on double or triple speed, I want you to slow it down, because this is where you're going to lose points on your lab write-up. The concentrations that you determined over there are going to be cut in half. Because if I take this liquid sample and put it in here, it's going to dribble all over the floor, right? So what I'm going to do is mix my liquid sample 1-to-1 with more hot agar and then put it into the little hole that I made, right? So all the calculations you determined over there need to be cut in half, okay? That's a key point. In the past, when we graded these, it was so hard to know what is what, but since everybody's data is the same, there's going to kind of be a right answer that we're going to be looking for. So if you're off by 2, this is the step you messed up. Okay? So how am I going to know which sample is which? Well, Petri dishes come with a lid, and if I put a little mark that goes with the lid and the bottom of the Petri dish, then I can just hold those two the same, and I can kind of label which sample is which on the top of my Petri dish. Okay, so might as well start with our most concentrated sample. So remember, this is 200 microliters. I'm going to mix it with another 200 microliters of hot agar. Now, this is room temperature, this is hot. As soon as I put this in there, the agar is going to start solidifying. I don't want it to solidify in my pipette tip, right? If you go and, but I also want it to be mixed well, so you kind of have to do this process pretty quickly. Pull up 200 microliters, quickly mix it without having air bubbles, and then add it to the sample. That's a little bit too much. See, maybe you can see how I kind of spilled it off to the side, but not too bad. Okay, so.
He's got a yacht. Yeah, he doesn't do this. I thought he's got a yacht.
So now let's do our 1 to 2. This again is 200 microliters. So I'm going to add another 200 microliters. Carefully mix it. And in it goes. Okay, my 1 to 5 dilution is too much, right? This is 500 microliters here. So I'm just going to transfer a little bit of this to a fresh tube. 200 microliters. (200 microliters of my hot agar. Give it a mix. And in it goes. So you can see how these are starting to be filled up. And so what I'm going to do is just continue to follow the instructions here on part 10 of your protocol to add the rest of my different concentrations. In addition, I'm also going to add samples of my 3 different sizes. Remember these? These go back to, oops. We made these on step 4, where we had different amounts of PBS, which caused us to make different sizes of particles and different amounts of particles. So we're going to look at these just as a 1-to-1 dilution of these, 200 to 200, and we'll also label those on there. So I'm going to fill these up. Okay, so I've added all of my samples to the Phantom. You can appreciate the differences in terms of the intensity of the whiteness with the different dilution factors. And I've got all my values recorded here. And so that way, when I give you the data, I'll have my labels correct. Okay? So the last step then is to put a final layer over the top that seals it. So I'm just going to pour this last layer. Really, the only thing you can mess up here is if you don't have enough or you get some air bubbles. But now this is going to be sealed, and we're again going to let it cool for a minute so it solidifies. Okay, so this is another one of those times where I just really, really wish that I could have you in the lab, because this is a really fun toy. And the first few years I taught this class, we had this ancient, awful ultrasound system. And I got this a couple years ago. I love it, the students love it. And this company is called Butterfly, if you want to read about them online. My student Yash was just telling me that they're going to go public in a few years, and I can see why. They're just a really great technology. Next to me is a kind of research grade ultrasound system, and you can appreciate just how big it is. So the ones that are used in the hospital are about this size. They may be slightly in nicer packaging, but compare that to this, I think really appreciates the value. So when you go into this system, there's a number of preset modes. So for example, cardiac, bladder, abdomen. And so if we go something that needs to be relatively deep, like imaging the heart, and select that, you can appreciate my axis on the right side. These are numbers in centimeters. So now I'm going about 16 centimeters deep. And I can adjust that by sliding up and down, okay? Sliding left and right changes my gain. And you remember from our discussion with the spectrophotometer that gain is just the additional potential that is put across the detector. So the exact same amount of initial stimulus is creating more signal here, okay? However, we don't need to image 16 centimeters deep, so we're going to go to mode called vascular access. So now I'm only imaging 3 centimeters deep, okay? Now I'm only really imaging 1 centimeter deep. Your sample is not very thick, so we don't need to go very deep. When you do ultrasound imaging, you need to have some kind of coupling media. And you may have seen this, for example, in obstetrics. When someone's imaging the fetus, they will put gel onto the person's skin. So why is that, right? I'm talking to you right now with sound pressure waves, and I don't need to put gel in your ear, right? But I do need to use this gel to couple the sound waves that are coming from this detector into the sample. And the reason is because these are megahertz frequencies as opposed to the kilohertz frequencies that I'm using to speak to you. So these megahertz frequencies need a medium to travel in that is more than air, that has a density more than air. So most people have a vein right there, myself included. So if I put the transducer on the vein, you can really nicely appreciate this black circle. You can appreciate the skin, you can appreciate the radius that's underneath it, and you can appreciate the skin on top. So at the very top of the image is my skin, big black circle is my vein, and then the white part underneath is my radius bone. This is what's known as a short axis view because I'm basically cutting my arm like this. Whatever plane you hold the transducer in, that's the direction that you're imaging. So I'm getting basically like my arm cut in half when I hold the transducer like this. If I hold the transducer like this, now I'm getting what's known as a long axis view. And so here, that long black tube at the top is the vein, and the radius is the black blur underneath it. What's really cool is that I think I can go to Doppler and image not my vein, but my artery. And so that black part that you see in the center is my radial artery, and that pulsing that you can see is actually the movement caused by my heart beating. So that's pretty amazing. Okay, let's see what we can do with your particles. So now we're getting ready to image your phantom. And so I'm I'm not going to put gel on this. That's going to be a big mess. I'm just going to immerse it in a water bath. This is basically thick water. So I've got a little piece of tape, and I'm going to use that tape to hold the sample at the bottom. And then I'm just going to gently pour some water. I'm going to hold it at an angle so there's no air bubble underneath. And so when I image, you can appreciate this area on your screen, which is now the particles that we just made. So we're looking now at a cross section. So the really white area at the bottom is the bottom of the Petri dish. You can see the layer that we poured at the top. This layer right here is the very top sealing layer. And then these are our different samples. Okay? And so one important thing is to get multiple fields of view, right? Because you want to have a mean and a standard deviation. So the only way to do that is to get multiple replicate images of each sample. Okay? So to be consistent, one thing that's easy to do is to just hold the transducer constant and then move the sample to be on top of the transducer. So one thing that's important is your gain. So you want to have your gain the same across all samples, okay? You don't want to have your gain artificially higher than others, or else your straight line won't be straight, okay? So if you think about imaging one of these holes, how do you do your replicate samples? Well, you could do one like this, and one like this, or you could do 1, 2, 3. It doesn't really matter, but what you do want to get is multiple images. So we're not going to walk you through each and every one of these image collection points, but what you are going to get is 3 images per sample that you can then use for image processing. Okay, so we're now in the basement of the SME building, and so this is yet another one of those pieces of equipment that I just really hate that you guys can't use. This came online about 2 years ago, and so this instrument is called the MANTA. I mentioned it at the introduction of the Day 2 section, so multi-wavelength nanoparticle tracking analysis. So it's kind of like dynamic light scattering, and it's kind of like dark field microscopy. So if you think about what we're doing in dark field microscopy, right, we can't necessarily see individual tiny nanometer sized particles, but we can see the photons that they scatter, right? This is known as the airy disk, if you've ever taken a microscopy course. And so that's why in dark field microscopy you can see objects that are much, much smaller than the resolution limit of the microscope. So what we're going to do here is simply look at scattered photons. And this technique has been around for a while in terms of conventional nanoparticle tracking analysis. What's unique about this system is that it has 3 lasers. And so if you think about at what wavelength does a particle scatter, well, the rule of thumb is that it generally tends to scatter at a wavelength similar to the size of the particle. So a 300 nanometer particle will scatter more blue light, and a 600 nanometer particle will scatter more red light, right? And so by having multiple wavelengths, we are sensitive to a broader range of particle sizes. And so that's what this instrument does. So we look we dilute our sample. That's one thing that's absolutely critical, is having the right dilution factors. Otherwise, all of those airy disks from different particles are going to overlap and there's no way to resolve them. So the dilution factor is really key. Tengyu He is a PhD student here in the department, and he's an expert user of this instrument, and he's going to show you in a little bit some more details about preparing the sample and how to get the dilution factors correct. But once you have the dilution factors correct, the instrument is analyzed, what you're going to see are these particles moving in real time due to Brownian motion. And similar to what you learned in dynamic light scattering, that Brownian motion is dependent upon the size of the particles. So therefore, we can back calculate with pretty high accuracy the size of the particles. So that in and of itself is great. But the other thing that this instrument does, which, I mean, this is going to be the third technique you've used how to size particles. You've done SEM, dynamic light scattering, and now this. So size is interesting. But what you can do with this instrument as well is you can count the number of particles, okay? Because you can individually count those little wiggling airy disks, and you know your illumination volume. And so therefore, by counting and doing the illumination volume, the instrument will give you the number of nanoparticles per milliliter. And so when I was demoing this before we bought it, I bought some calibration particles from Nanocomposites, and they had determined the concentration in terms of particles per ml to 3 decimal places. And I put it in the instrument and it got it correct to 2 decimal places, comparing reference materials that were counted by inductively coupled plasma and TEM. So this is a pretty powerful technique. If you think about what else could you use you put a sample in and it tells you, oh, you have 10 times 10 to the 12th nanoparticles per ml. That's a pretty powerful tool to have. Now, if you'll recall when I talked about concentration, we talked about another way to determine the number of particles per ml, right? We talked about using the concentration in milligrams per mil, the volume of one particle, and the density of the material to back calculate how many particles per ml we have. So this is going to be an exercise is to kind of compare how similar are these two samples, or excuse me, these two ways of determining that value of nanoparticles per ml. Okay?
So now I'll be demonstrating how to use MANTA to measure the size of 3 silica samples we synthesized. So the 3 tubes contain 3, it's supposed to be 3 different sizes, and we will confirm these later with MANTA. Here is a cuvette I'm going to use. It's made of quartz, so you can see forwards transparent walls. Now I'll put in the stir bar. I will explain why we need stir bar later, and then insert these black things, which is designed to stabilize particles later. Now I will start from the smallest particles. I'm going to transfer this particle solution to the cuvette. I will take I'm going to take 1 milliliter of this silica particle solution. And then gently there will be some bubbles, if there are bubbles, and we have to mix it a little bit with the pipette to make sure there are no bubbles in in that window we are going to image. Maybe shake it a little bit. Okay, now our bubbles are all gone. And I will make sure the walls are clean, so there will be no light scattering induced by contaminants. Okay, next step, I will insert this cuvette containing the particle solution to the instrument. So this is called MANTA View Sizer 3000, provided by Haribak company. And we want to show you how the inside look like. So in that direction, excuse me. So in that direction, there's there are 3 different lasers embedded, built in, and then in this direction, there's a microscope. Now I'm inserting this cuvette to the instrument, and then put the lid to protect laser from coming out, and then close the lid of the instrument. The software the software we'll be using is called ViewSizer. The nice thing about this technique is that there are actually many different modes for different applications. Today we'll be using NTA, which means nanoparticle tracking analysis, and like other modes here are like full fluorescence. This is designed to see fluorescent beads or particles of different colors. Kinetics means in this kinetics mode, we can actually measure how the light scattering be increasing or decreasing because of the particle growth, or in some cases, people will use this for protein to study how protein aggregates. The sync float mode is just a different way to measure the particle based on the gravity effect on particles, because for some larger particles like 10 micron, then particles can be sinking down, and then and how fast the particle will be sinking is related to the size of the particle. With that being said, we'll focus on NTA for this time. So I'm gonna input some information for the sample. Let's call this sample as 25 microliter. And a key information we need to input for this software is to choose what diluent we use, because this determines the viscosity of this of the sample we measure. And I think Professor Jjokerst will introduce will introduce the principle of this technique, and viscosity is one main parameter for this measurement. And in our system, recall that we use water, so we just select water. And then temperature is the second parameter we need to determine. This machine can actually control the temperature from 10 to 50 degrees C. So I will just put temperature as 20 degrees C, and then make the temperature hold at 20 degrees.
So what you're seeing now is this is the 25 microliter sample, the one where we added 25 microliters of PBS and created the smallest nanoparticle size that you made out of the 3. And what you can appreciate here are these little nanoparticles wiggling around due to Brownian motion in real time. And so as you look at the different videos that we're going to give you videos for the 3 different sizes. I think you'll appreciate that the amount of movement of the bigger particles is going to be much lower. So these particles are moving pretty rapidly. So due to the amount of movement, we're going to determine the size, and based on the number of spots of light, we're going to determine the concentration. So I just think this is really neat. I hope you do too, that this is, we're imaging these particles in real time. It's kind of, you know, we don't have the resolution of electron microscopy, but they feel kind of alive. And so this is a really neat technique.